In the last lecture, we discussed about fluid properties. We talked about density. So just to recall what we have done in the previous class. So density is mass by volume. Specific weight, we defined it as weight divided by volume. So that is mg divided by v. And mass by volume is rho, so we call it as rho g. Then we said specific gravity is density of the liquid divided by density of the water. Or if it is going to be a gas, then we can say, so the subscript, we can say S of liquid and S of gas. So that is density of the given gas divided by the standard gas is air. So density of air. And we also looked at specific volume, which is by M. Okay, we also looked at viscosity. Mu is dynamic viscosity, and it is defined as shear stress divided by the velocity gradient or the rate of shear strain. So shear stress divided. And we also looked at kinematic viscosity. Kinematic viscosity is ratio of dynamic viscosity divided by your density. Okay. So just like we had the unit for this viscosity, dynamic viscosity is Newton second per meter squared, or we poise. Okay. So centipoise can be represented as Cp and poise can be represented as small p. Okay. This kinematic viscosity, apart from your meter squared per second, it can be denoted in meter squared per second. Apart from that, it can also be represented in terms of Stokes. So 1 Stokes is equal to 10 to the power minus 4 meters squared per second. So 1 centi-Stokes, that is going to be 1 by 100 times of your Stokes. So that is going to be 10 to the power minus 6 meters squared per second. Okay. So let's move on to the next topic, which is Newton's law of viscosity. So this is very, very simple. Newton's law of viscosity simply tells you that the shear stress is directly proportional to the rate of shear strain, or the velocity gradient, or the rate of deformation. So to replace this constant of proportionality, we have introduced the proportionality constant mu, which is called as your dynamic viscosity. So this dynamic viscosity mu is the proportionality constant. And so your tau is mu times du by dy. Okay. Of viscosity where your tau is proportional to du by dy. So if at all your shear stress is proportional to the rate of shear strain, then the fluids which obey the Newton's law of viscosity are called as Newtonian fluids. And there are those Newtonian fluids. Okay. So Newton's law of viscosity very simply tells you that the shear stress is directly proportional to the rate of shear strain. Okay. And then we will look at the types of fluids over here. So that is graphically also it is represented. So we will look at the ideal fluid. So if it is going to be an ideal fluid, you can see that this is your increasing shear stress. Shear stress is going to be your tau. Okay, tau is your shear stress. So if it is going to be this line, in this line, your tau is going to be equal to 0. So if you look at ideal fluid, an ideal fluid does not have shear stress at all. So if there is no shear stress, so what we know is mu is equal to tau divided by du by dy. So 0 by anything is going to be equal to 0. So if shear stress is 0, then viscosity is 0. So ideal fluid is a fluid which does not have any viscosity, and at the same time, it is incompressible. When I say incompressible, it means density is held constant. Density doesn't change. When you compress something, density changes. When you say it is incompressible, that it is not possible to compress something. Okay, take water. If it is a gas in a cylinder piston arrangement, I will be able to reduce the volume of the gas. But if it is going to be water, I will not be able to do so. Okay, so water is an example for an incompressible fluid, any liquid for that matter. So fluid which is incompressible horizontal line which identifies itself with the x-axis, that is your ideal fluid. And it is very clear that this fluid is going to be an imaginary fluid because none of the fluids in nature are going to be inviscid, non-viscous fluid. So we use a term called inviscid. This means non-viscous. Non-viscous is nothing but your viscosity is equal to 0. Okay. So all the fluids in nature, they are going to be real fluid. A real fluid is a fluid that possesses viscosity. Okay. Newtonian fluid and non-Newtonian fluid, we have already seen that which obeys Newton's law of viscosity, where your shear stress is proportional to the rate of shear strain. That is Newtonian fluid. And if it is not proportional to the rate of shear strain, we call it as non-Newtonian fluid. Additionally, we have something called, so that can be seen here in the graphical representation as well. So the Newtonian fluid, you can see that shear stress, as shear stress increases, the velocity gradient increases. So this is your Newtonian fluid. And in this case, you can see that there is a variation over here. It is no longer a linear relationship. Then it is going to be a non-Newtonian fluid. It is not directly proportional. Okay. And then we have this ideal plastic fluid. This is a fluid in which the shear stress is more than the yield value. And at the same time, the shear stress is proportional to the rate of shear strain. Okay. So here the shear stress is more than the yield value. You can see that the line starts over here. For a Newtonian fluid, it starts over here from the shear stress is equal to 0. So as shear stress increases, your velocity gradient increases. However, for this particular ideal plastic fluid, the shear stress doesn't start with 0. The shear stress has got a value which is more than the yield value. And thereafter, you can see that the shear stress is proportional to the. And when you take an ideal solid, you can see that there is no velocity gradient at all. Okay. So for this, so let's spend some time over here to identify the difference between so let me consider a surface, and on this surface, so this is a stationary surface, and that is what is indicated by this hatched line over here. So let me rectangular elements. I have got a rectangular element. Assume that this is a rectangular element, although it's not perfectly rectangular because I'm not able to draw. So I'm not able to draw it as a rectangle. Now it looks like a rectangle. Okay. So now if I apply, so this is going to be a rectangle, which is stationary and it is kept on a fixed stationary plate. If I apply a shear stress over this, say I'm going to apply a shear stress value of tau. So what will happen? So if it is when a shear stress is applied, so this surface, this is not going to change because it is lying on the floor, but it is no longer going to be a straight line. Initially, it was in this particular position, isn't it? That is how the rectangle was. Initially, it was like that. Now you can see that once the shear stress is applied, this particular region has shifted over here. and this straight line has shifted over here. So when I apply shear stress, so there is a change in this angle of inclination. Previously, it was 90° over here. Now the angle of inclination has changed. Okay. So this fluid, this element, or a liquid element. Okay. When it is within the elastic limit, your solid is going to deform. That means the shape of the solid is going to change. If I further apply shear stress, if it will deform totally, it will break. Okay. Whereas if it is going to be a liquid, your liquid, see, initially applied shear stress, it shifted to this new position. And now when I apply further shear stress, it deforms further. If it is going to be a liquid, it is going to be deforming further. Okay. So as I apply shear stress, there is going to be a continuous deformation in case of a liquid. Whereas if it is going to be a solid, there is no continuous deformation. There will be a deformation till the elastic limit. Once the elastic limit has been reached, and when it is overtaken, the solid deforms permanently. That means it breaks at one particular point of time. So this shear stress, according to our Newton's law of viscosity, that is proportional to du by dy, and that is what we call as Newtonian fluid. And if it is not proportional, it's going to be non-Newtonian fluid. So there is going to be a velocity gradient in terms of a liquid. If it is going to be a solid, there is no velocity gradient within this solid object. So this du by dy is going to be equal to 0. So your ideal solid represents a vertical line, which is nothing but your du by dy is going to be equal to 0. Okay. So this is a slide that tells you about the different types of fluids. Now let's look at a couple of problems. Now in this particular example, equal to 2 by 3 times y minus y squared, and u is the velocity in meter per second at a distance y meter above the plate. Determine the shear stress at y equal to 0 and y equal to 0.15 meter. And they want us to take the dynamic viscosity of the fluid as 8.63 is equal to 8.63 poise. So what we know is 1 poise is going to be equal to 1 by 10 times Newton second per meter squared. So 8.63 divided by 10, which is 10 per meter squared. So we can convert that to SI units. And what is given to us is U, and they have said that it is 2 by 3 times y minus y squared. And they want us to find out the shear stress. So what do we know? Shear stress is mu times du by dy. So that is what the Newton's law of viscosity tells us. So they want us to find tau, and they want us to find that tau at y equal to 0. So which means it is mu times du by dy at y equal to 0. And they want us to find tau at y equal to 0.15. So which means mu multiplied by du by dy. And this du by dy should be evaluated at y equal to 0.15 meters. So we know the value of u. So what is du by dy? We have to differentiate u with reference to y. So that is 2 by 3. So differentiating y, we get 1. Y squared, when we differentiate it, we get it as 2y. So now what we require is du by dy at y equal to 0. So this is the value of du by dy. Let us put a box over it. So what is the value of du by dy at y equal to 0? simply minus 2 times 0. So that is going to be 2 by 3. What about du by dy at y equal to 0.15? So that is 2 by 3 minus 2 times that is going to be 3. So 2 into 0.15, that's going to be 15 into 2 is 30. So that is going to be 0.3 or 2 minus 0.9 divided by 3, that is 1.1 divided by 3, or points. How much is that? 3 threes on 9. And so it is 0.366. Okay. So it is, the unit is going to be meter per second by meter. So it is second to the power minus 1. Okay, so if we substitute it over here, the value of mu is 0.863 multiplied by 2 by 3. And this is 0.863 multiplied by 0.366. So if I use the calculator over here, so it is 0.863 into 2 divided by 3 is 0.57 Newton per meter squared. And the other guy is 0.863 into 0.366. And this is 0.316 Newton. Okay, so that is the value of tau at y equal to 0 and y equal to 0.15 meters. Okay, so we could have used the space here. The next one, a plate points at 60 centimeter per second and requires a force of 2 Newton per unit area to maintain the speed. Determine the fluid viscosity between the plates. So now what they have said is there are two fixed plates. There is an upper plate and a lower plate over here. And they are separated by a distance of y equal to 0.025 mm. And sorry. So what should have been done here? They say that so this is not a fixed plate. This plate here, it moves with a velocity of 60 centimeter per second, or we can call it so this plate over here, it moves with a velocity of 0.6 meter per second. And it requires a force, the force that is applied over here. So that is 2 Newton per unit area. So it is Newton per So determine the fluid viscosity between the plates. So what is given to us is the speed of the plate is given as 0.6 meter per second. The distance is 0.025 mm. Let's say 2.5 into 10 to the power minus 5 meters. Okay. And then the force is given as 2 Newton per meter squared. And they want us to find the value of mu. So what we know is tau is mu times du by dy. Tau is mu times du by dy. So mu is going to be tau divided by du by dy. So if this plate is going to move at a particular speed, then the fluid is also going to move at that particular speed over here. Okay. So the fluid on this particular plate, that is going to be zero. The velocity of the fluid at this particular point is going to be equal to zero. And the velocity of fluid at this particular plate, that is going to be 0.6 meter per second. So your du by dy is going to be 0.6 divided by 2.5 into 10 to the power minus 5. Okay. And what is this tau? This tau is going to be force per unit area. And that is what is given to us over here. This is actually so F by A. So what is given to us is actually the tau, which is 2 Newton per meter squared. So all I have to do is directly substitute it over here. 2 divided by 0.6 divided by 2. That is going to be 2 into 2.5 into 10 to the power 5. Oh, sorry about that. This guy is going to be in the denominator, only the, yeah, that's fine. I can take that too. So this is 2 divided by 0.6 into 2.5 into 10 to the power minus 5. So if we use the calculator over here, so 5 divided by 0.6, that is 8.33 into 10 to the power minus 5. So it is going to be 8.33 into 10 to the power minus 5 Newton second per meter square. Okay. So that is the answer that we get for the dynamic viscosity of the fluid. And we will stop here, and in the next video, we will continue this. Thank you.